Well, welcome back, everyone. Today I'm honored to be joined by Dr. Bill Robinson. Thank you so much for joining me. Talk to me about chaos theory.
Yes, chaos theory. Right. So I'm a mathematician. When we talk about chaos theory, we're talking about a mathematical type of model.
Right.
And the classic example is weather. And the story goes, there was a man trying to get a computer to predict the weather. And so he developed his model. He put in all these parameters, and he kicked off the model running. So he started doing these computations. But he had to stop the computer and leave and then come back. And so he tried to do that, but the model kept running, all right, and gave one set of predictions. Said, "Whoops, I need to go back and restart from this same point, so I can verify my results or something." And he put in the same conditions, like the model had reached an intermediate step. He put in the same conditions and kicked it off running, and somehow the model predicted with the same starting point. So we thought the model predicted something completely different. It's going to be sunny or it's going to rain. He said, "What? This is deterministic, right? Like I wrote all these rules." And he found out that because of some tiny little rounding error, the computer was storing 0.325678, but it had rounded and it was really like 0.799.
Right.
And that little rounding error inside the machine was enough that at each step of the calculation, the error got magnified and magnified and magnified, and somehow a tiny little change in the measurement gave completely different results. And so this is where we get the idea of a butterfly flapping its wings in China changes the weather patterns here. You can think of a system that has some chaotic behavior. Would be like if you're rolling a marble from the top of a mountain. Right. So you change the initial condition a little bit, and if you move it an inch this way, it's going to roll down to that valley. And if you move it an inch this way, it'll roll down into this valley. And so this is chaos theory. It's systems that have kind of increasingly divergent behavior, even with very similar initial conditions or unpredictably different outcomes based on very small perturbations in the input.
Got it. So it would be possible to predict something like the weather if you had a perfectly correct set of data and it didn't change. Like if you went all the way down to the last decimal place, whatever that is, and it didn't ever round.
If you could tell me what the last decimal place is, I'd love to know.
Okay.
So I think the idea to keep in mind is if you put a sensor, maybe one sensor at every cubic inch of our atmosphere,
okay,
and collected data at every little square cubic inch of our atmosphere, that's not enough, right? So you can feed that into the model, and for a while it might be very, very good, but the principle will take over eventually that whatever you didn't measure is going to cause some kind of crazy perturbation. That's the word. Like perturbation, meaning just a very, very small change. And you needed that information to accurately predict, right? There's always that piece of information you don't have that you're going to need to predict.
Yeah. Now that feels like not that big of a discovery. That if I started out a math equation and I got my number wrong at the very beginning, it's going to have huge impacts on the later numbers. What made this a big discovery?
Okay, sure. Yeah. I think the idea is that the magnitude of the divergence, what you're trying to predict, doesn't seem to match the magnitude of the divergence in your measurement, right? So you would think when you're measuring something, when you're doing science, you think, I'm gonna measure the amount of liquid. I'm doing a chemistry experiment. I'm going to measure the amount of liquid and I'm going to add it to this powder or something. And as long as I'm close enough in my measurement, right, then it should do the right thing.
Right.
But the idea here is you can't get close enough because you can't be perfect. And so you can never control the long-term behavior.
Right.
So no amount of precision in your measurement is going to equal precision in your your actual outcome.
What type of systems allow for chaos theory? Because obviously not all of them. There are some things, like you mentioned, chemistry,
Right.
that like, you put in 1 point something milliliters, you can expect that decimal point to be the deciding factor.
Right. Well, that's a good question. A really interesting one is the motion of the planets. And so we're familiar with the story of the model of the solar system. And we have the geocentric models, and discovered there's actually the Earth revolves around the sun, and we have Galileo and Kepler and all the rest. We have Newton, who comes along, develops his mathematical framework for the theory of gravitation, seemingly predicting what the planets should do, and they go in elliptical orbits. So the only problem is that's only true if you have like two planets or a planet and a moon. Like if you had the Earth and the moon and nothing else in the universe, then that's great.
Yeah.
But as soon as you have the effects of other planets' small gravitational pull at that distance, they don't go in elliptical orbits. They go in almost elliptical orbits. And what happens, if you put up a sheet of paper big enough for a planet to pass through, and you stretch that out right along the trajectory of a planet, what you would find is it would go through a hole, and the next time it came around, it would not go through the same hole.
A slightly different hole.
It would go through a slightly different hole, and predicting where exactly it's going to be is nigh on impossible, certainly long term. Right. So because there's some kind of chaotic behavior where all these effects line up.
Right, because Jupiter has X amount of moons, and the moons pull it slightly one direction or another. Right. Got it. Okay. And so it has basically the only systems that this applies to our systems was large enough data points where... And
actually, let me just say, what's interesting in this case is although there's this unpredictable behavior, I'm kind of like shifting a little bit. So when you have unpredictable behavior, so a chaotic system is very hard to predict because of that effect.
Right.
And but what's interesting with the planets is that they still almost go in ellipses, right? So even in a chaotic system, you can find general trajectories that kind of qualitatively describe or approximately describe the behavior. So maybe we aren't expecting Neptune to fly off into space. Right. So it's not that we expect anything to happen, but we can't predict what exactly will happen.
With pinpoint accuracy. Got it. And only systems that are large enough. So is there a threshold at which point a system becomes unpredictable to pinpoint accuracy?
Right. And I forget what our current threshold is for predicting the long-term behavior of the solar system. And we have supercomputers that can do so many computations so fast. I'm trying to think how far out in advance we can predict lunar eclipses. Maybe it's 1,000 years or 5,000 years or 10,000 years, but it's not a million years.
Right.
So at that point, is the moon going to pass in front of the sun or not? We don't know yet.
What are the real world applications for the chaos theory and kind of understanding the limitations of our current technology?
The real world applications. So, So if you know what you know and you know what you don't know, that tells you what kind of predictions you're authorized to make.
Right.
And so that's kind of it helps you have the right framework for your models. Maybe you could think of some of these things that are very hard to define with pinpoint accuracy, but you can define kind of the general behavior would be the behavior of a gas, of course, right? So if you put oxygen inside of a balloon, you can't tell where one molecule is going to end up.
Right.
After a few minutes or less, of course. That's fine. But you know that basically the air is going to fill the space. Right.
You can give a broad generalization.
And so if you kind of know that's how the system works, then you are going to use the right tools to analyze it. Instead of trying to come up with a computer program that can tell you where the molecules of oxygen go or carbon dioxide or whatever.
This feels like something that could be helped by quantum computing. Is that correct, or am I wrong in that?
So what you're saying is if we increase our computing power enough,
Yeah, well, and my understanding of quantum computing is that it's, I don't know if you're an expert in this,
I am not.
but my understanding is it's basically like it can do all of the equations at once. And in other words, if there's a maze, a normal computer kind of tries out every route, every single route. A quantum computer, as soon as it reaches a fork in the road, tries both forks.
Okay, yeah.
Would quantum computing help with understanding more, with increasing that threshold?
Right. So I don't know what the hope is or the theory behind quantum computing exactly. I mean, I've heard a little bit about what you're talking about, but let me just like talk through what that challenge of the problem is. So if you want to predict everything that's going to happen, and you want to have a computer that can do that, well, in theory, you have to predict what every, say, electron does.
Right.
Well, and then I guess you're going to need a computer that's at least that large, right? So you're going to involve every electron in the universe in making the computer that can predict where all the electrons go. Now, if you think that I'm exaggerating the effect of an electron, there's this great book by Ivar Eklund, Ekland, I think that's how you pronounce his name. He's written a bunch of books that are really good, popularized complex mathematical topics. And I remember reading in one of his books, if some devil on the far side of the universe wanted to mess with what's going on Earth, he could move an electron in a distant star, and what would happen? Well, think of a game of pool, right? Billiards. Billiards display this kind of chaotic behavior,
Right.
this divergent behavior. So if you move your cue just the slightest amount, the first ball will change its trajectory in accordance with how you move the cue, right? But as soon as you have contact with another ball, right, a collision, the other ball is going to be very sensitive to where the first ball hits it,
Right.
right? So if you just move your cue that little bit, that completely changes the direction.
It's a
of the
wider
second
divergence.
ball, right?
Yeah.
Well, what if there's 3 collisions?
It increases
Again,
exponentially.
and it increases. And so I believe, I can't remember the exact numbers. I think after the 10th ball gets hit, the gravitational fields exerted by the people in the room have a measurable effect. And by the 52nd or 53rd, the position of the electrons at the far side of the known universe have a gravitational effect on the outcome of that shot.
Now that is nuts.
Right. So if you think of the gas in a balloon as a bunch of billiard balls, except it's not just one, it's hundreds, thousands, millions.
Right.
Right. And each of them are bouncing off of each other. Right. So if you want to try to predict what's going to happen, you have to account for everything in the universe.
Got it.
So I don't think even in theory we could ever hope to come up with a computer that's going to do that.
Yes. And I don't know that there would be a purpose to knowing all of that.
Right.
Is that correct?
Well, that's right. Yeah.
Yeah.
And that's why the strategy is not to predict motion of individual particles. It's to kind of define or analyze their kind of qualitative behavior.
Got it. And there's an old theory that if you could know all of the data points in the universe, you could predict what's going to happen next. This is getting at that in the sense that like.
Okay, right. So that raises a whole nother philosophical question, which is even if some alternate universe there was a computer that was big enough to predict the outcome of our universe, right? So,
right.
Is our universe deterministic anyway? Right. So is it computable, or did God create the universe with some kind of uncertainty? Whether that's quantum uncertainty or kind of like this physics natural uncertainty, or are we talking about human will? Right. So could it even theoretically a computer predict, what I'm going to choose to say next?
Right. Potentially.
That's not a mathematical question.
Yeah.
That's a philosophical question. I think the answer is no.
Right.
I don't think that we are deterministic.
Yeah. We'll get into this a little bit later because
Okay, great.
we're more curious about that. This theory that the billiards ball theory, I'll call it for sake of ease, would it have implications for nuclear warheads as they're thinking about
Probably.
splitting atoms, or nuclear fusion as they're thinking about conjoining atoms together?
Right.
Calculating that feels like it's a similar game to the billiards balls.
Of course, there has to be in some sense, right? You can't predict everything that's going to happen when you split an atom,
Right.
but you want to predict generally what's going to happen.
Yeah.
So yes, I imagine that would be a good application of this idea.
Yeah.
Right.
What are the philosophical implications of the chaos theory?
Well, a healthy dose of humility for us trying to explain everything. Yeah, I mean, I think so. Anytime you can look at math, and math tells you something about the way the world works, right? Math, and then physics and all the other sciences that use math to describe the world. And to me, this raises some limitations on our knowledge and our expectation to what we can know and predict with mathematics.
Right.
And so I think God used math. Math is. We're thinking God's thoughts after him. I think he made the world according to, the mathematical blueprints that we can uncover. But I also don't think that we can reduce the universe to some Pythagorean mathematical number. System.
Why do you think that is?
Why is the creation more than just math?
Yeah.
Why is God so big? I think we're focusing in on one aspect of how God's creation is, and therefore in some sense how God is. But math isn't trying to tell you everything.
Right.
Right. If it starts to try to tell you, how then can we be saved? Well, you're not doing math anymore.
Yeah.
So it's just like we've narrowed our focus to a set of questions, and if math tries to, science or history or anything tries to answer questions that are outside of its scope, then it ceases to be what it claims to be. And math is talking about one slice of experience and reality.
Yeah.
It's a big slice, I think, but it's not everything.
I was going to ask, what's the limitations of mathematics, and how does those limitations help us understand the world we live in?
Well, that question could go in a lot of ways. So you can talk about axiomatic systems and Gödel's theorems and inherent limitations on mathematics itself, kind of like as a system or a logical system, but so that's one direction you could talk about. But there's also just how do you, whatever mathematics you have, how do you connect it to the real world?
Right.
Right. So mathematics, I guess, is something that we do in our heads. It's a mental activity. And so the question is, why is this thought process that I have in my mind about quantity, why does that align with reality? And if that's what we mean by truth, that whatever we're doing mathematically is true if it accords with reality, well then it's kind of a challenge to say, why is it that this kind of technique we invent, calculus, right? Or the notion of different levels of infinity or something like that. Why is it that's, in what sense is that true or false? And why do we expect these computations? We collect data, we pull it into the mathematical world, right? So you measure distances and you assign numbers to those and you write them down on the page, and suddenly you're doing math with them, right? So you've taken it into the mental and you say, well, I have rules about adding numbers and dividing numbers and integrating functions and things like that. And so I pull it from the real world into the mathematical mental world, and then I do math, and then I want to predict. I want to say something back about the real world. Well, there's a translation there into math and out of math.
Right.
So I'm not sure that that's strictly speaking a mathematical, like the translation process itself. Math has something to say about that. Mathematicians have to deal with that question intensely.
Right.
But why is it that you can use math to describe the real world is a philosophical question. Actually, it's a meta mathematical question.
Yeah.
Let's talk about math and
Right.
its suitability.
As opposed to by math. Yeah. And this has real world implications for how people understand free will, and the actions that they take. How should you view your life and the actions that you take in light of the fact that it's all a bit chaotic?
I think that you can try to start looking at what math says about the world and chaos theory and probability and statistics, and you can try to look at that and infer, philosophical truth. It's not that can't lead you to some truth, but I think that's the wrong direction.
Right.
Right. And so God has revealed certain truths to us in Scripture, and I think that might be a safer starting point if we want to understand God's sovereignty and our responsibility, and to reason theologically rather than mathematically try to tell theology what's going on with our free will and our responsibility and God's sovereignty.
Yeah, understand that there's an order to this figuring out how things exist.
Sure. I think mathematical concepts and questions and in discoveries can bring color and insight to that conversation. But I don't think that's the place to go for the answers to those questions.
This all ties into
Did you get a theologian on here?
Yeah, this all ties into the infinite. Where did humans first kind of come across the idea of the infinite? Because that seems like a bit of a bizarre notion.
Right. The history of the concept of infinity. I have actually a really great book that talks about kind of early cultural views on infinity. So I don't remember. I would never say first. We often go to the Greeks when we start talking about the birth of Western civilization or mathematics or something like that. And so the Greeks began to wrestle with the concept of infinity. I don't think they were the first, but they were. They talked a lot about it. My impression is that they had they were actually. It was a negative. It was a pejorative word. The infinite was aligned with chaos and disorder. And so there was, we sometimes think of like the infinitude of God. God is so great. And it's a positive, like, I'm so glad we have an infinite God. And for them, there was something like disorderly and chaotic and scary out there about infinity. And so that's, I'm remembering back to something I read. Mathematically, okay, so one of the famous theorems that Euclid presented a proof of is that there are infinitely many prime numbers. All right, so that's before that, that there's infinitely many numbers. And what do you mean by infinite? You mean not finite, right? It's a negative term. So we know what finite is, I guess. It's you can count it.
Right.
At least in theory, you can count it. And so infinite is like not that. Whatever's bigger than that was not countable.
Right.
And so there's no biggest number, because if you tell me what you think the biggest number is, I'll say that plus one.
Right.
Right. But the Greeks did things with infinity, like saying the prime numbers are infinite. And so the concept of infinity just emerges naturally. I mean, if you have a son you're teaching to count, he's going to count as high as he can, right? And my daughter already counts to 100 in about 5 seconds, it feels like. And it raises the question, how high can you go? What's the biggest number? And then you start. It's like the most natural thing in the world to start wondering about infinity. And what turns out, I forget who said this, but the hunger to understand infinity, the concept of infinity has motivated and inspired more mathematical discoveries in every field than any other concept. Somehow when infinity comes into the picture, it raises many important questions. So Zeno's paradoxes is another example. If you remember, there's several of those. One of them is, how can you cross the room if before you get to the other side, you have to get halfway there. But once you're halfway there, if you want to go the rest of the way, you have to go half of the remaining distance.
Right.
And before you can go that last quarter of the way, you have to go half of that distance. And if you continue that thought process, you have to do an infinite amount of actions
Right.
to cross the room.
You never get fully there.
And you can't do an infinite amount of things in a finite amount of time, obviously. And so you can't cover distance. You can't cross the room.
Yeah.
So there's, the idea of the infinite creates many questions. It's a very fruitful concept. And even if it seems silly or paradoxical, trying to understand actually rigorously what's going on, or how do you make can you formulate that question rigorously, and if so, can you answer it, is like very productive.
Is it partly because it is so absurd that it kind of brings around this curiosity to, all right, let's see if we can delve deeper?
Yeah, and well, the idea is hopefully it's not absurd, meaning it's not contradictory or meaningless, right?
Right,
so,
meaning more
but it's a big concept.
Wild. Yeah.
It's wild,
Yeah.
right? Yeah. So it's a big concept. There's so much to it that it just like explodes your possibilities.
Yeah.
Right. So with calculus, you have the infinitely small, right? The infinitesimal. You have the infinitely big. You have Cantor, who talked about different levels of infinity. This plays out into all sorts of interesting directions, mathematically speaking, through the ages.
Yeah. What are those different levels or kinds of infinity?
Yeah. Right. So the idea of different levels of infinity is like, okay, we know what it means to count things. You assign a number to them in order, right? So if I think there's 10 objects, that means then I'm going to take a label 1 to the first one and a label 2 to the second, and up until I labeled the 10th one 10, right? So I say there's 10 because that's where I got to. And Cantor took this idea and he said, all right, so let's count infinite sets. And so you talk about the natural numbers like 1, 2, 3, 4 to infinity, like all of them,
Right.
1 plus 1 n plus 1 all the way up. And he said, all right, well, I would like to count things where there's my yardstick, right? So if I want to count sheep, I line up 10 sheep and I line up 10 numbers, right? If I want to count an infinite set, say the even numbers, that's an infinite set.
Right.
Can I line up the even numbers with the natural numbers? Right. So I have on one side I have 1, 2, 3, 4, 5, 6, 7, 8, and here I have 2, 4, 6, 8, 10. Right. And he said, look, if you take the 1 over here and put it next to the 2, right? You double each of them.
And the
you
2
take the
next
2
to
to
the
the 4,
yep.
and the 3 next to the 6. Then I can show, we call it a 1-to-1 correspondence.
Right.
Meaning I just counted the even numbers with the natural numbers, so there's the same amount of numbers.
And yet,
there are numbers in one set that aren't in the other.
right.
So one is strictly contains the other one. The natural numbers contain all even numbers and more, and yet they're the same size.
Right.
So that's his notion of countably infinite, is countable. A set that you can do this to is countable. If you want to do the negatives, add in the negatives. So not just from 1 up to infinity, but also 0 and -1. And he's like, well, alternate. 1, -1, 2, -2, 3, -3, and number them that way, count them that way. And so there's the same amount of, integers as there are natural numbers.
Right. Which makes it feel a little bit more like a get out of jail free card. Like we don't fully.
Well, it might make you think that this is just saying infinite sets, there's infinitely many things, so they're all countable in this weird infinite way.
Right.
And so some of the harder things to count, you might like the rational numbers or the fractions.
Right.
And there it feels like, well, to get from 1 up to 2, actually there's infinitely many fractions in between there, right? 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, right? And many more. Cantor showed that those are actually countable. So even though there's vastly more rational numbers than integers or than natural numbers, there's the same magnitude in terms of infinity, right? The rationals are countable,
Right.
countably infinite. And but the punchline of the story is that when you go beyond rational numbers to the irrational numbers or the real numbers, these are numbers that can be represented as decimals. And these include all the famous numbers like pi and e and things. They include square root of 2, things that are not rational, don't have a fraction representation. What's shocking is that that's actually a new type of infinity. So no matter, he proved in a brilliant argument, he proved that you can't count the real numbers using the natural numbers, right? So if it's not just that like, hey, I tried and it didn't work, right? Like I thought this would be a good system for counting the real numbers and finding a first real number and a second and a third, and he showed, he's like, no matter how you try, he proved it can't work.
How did he prove that?
So he said so he used a proof by contradiction, which is a way of saying, let's assume you can count them, and then that's our starting point. Let's assume that it's actually possible to count the real numbers in this way, line them up with the naturals, and then he showed that leads to a logical contradiction. So that's
in what way?
Well, he said if you had such a system of assigning 1 to a real number and then 2 and 3, it's hard to explain without a board, with a nature show in the back.
Yes.
But basically he said, well, all right, start listing them out, all the real numbers.
Right.
What you've done is you just put them in order with 1, 2, 3, 4, 5. Now, take that counting system, right? And let's like look at that counting system and use that to write down another real number. He said, so like on the first number you came up with, it's 0.1, 2, 3, 4, 5, 6, an infinite decimal, right? And he said, all right, so the first decimal point is a 1. Now I'm going to start writing down a new number, and I'm just going to change that 1 to a 2. Right, so I have 0.2 now. He said, but I'm not done. I want to look at the second number of my list. All right, and that decimal is 7, 8, 9, etc. 7, 8. All right, 8 is the second decimal. My second number should not have an 8 in the second decimal. All right, so I'm going to make that a 9.
Right.
All right, so in other words, he goes through this ostensible list of real numbers of decimals, and he changes one digit at a time, and then writes those digits, and that's a number.
Yeah.
Right. So that's a new decimal.
Right.
Now, the question is, you've just like written down a number. Is that number, does that have a place in your list? Right, because it has to.
Yes.
You just numbered all the real numbers, so it must show up on your list somewhere.
Right.
Right. Whatever number you can think of, it has to show up on your list. Now, is it in the first number? No, because I changed the first decimal.
Yeah.
Is it the second number? Well, no, because I also changed the seconds, so it can't match the second number. And I changed the third decimal, so it can't match the third number. And I changed the fourth decimal, so it can't match the fourth number. And in fact, I've written down an actual number in my head. Like I've described a way of writing down a number,
right,
as precise as you want, that can't be on a list of real numbers.
Simply because you can't go back far enough. Correct.
No matter how far you go, it's always going to not be on the list because you've changed each decimal spot.
Right.
So it's, again, if I could write down on a whiteboard, that might help you like visualize it better. But that's the core of the argument. No matter how you try, it's doomed to fail because we can always find a number that doesn't fit on your list.
Got it.
And so we have countably infinite sets and we have uncountably infinite sets that have just like, it's like a bigger infinity.
Got it. Okay. And what is that useful for?
So it seems like we're just playing games, I guess.
Yeah.
Right. So there's different ways to answer that question too. I would say this. The reason that mathematicians pursue answers to those questions is they want to make sure what they're doing is the right thing. This is one answer. So calculus, Newton, Leibniz invent calculus. We use calculus in everything. Anytime we're describing motion, right, or speed, or a million other things, we're using calculus. Calculus depends on the concept of the infinitely small or the infinitely close, right? And so, well, why are we allowed to talk about infinite things that don't end, things that seem to go on forever? Well, let's make sure that we have a coherent concept of the infinite, right?
Right.
And so you start to try to have logical rigor in any of the mathematical ingredients in your theory. Well, as soon as you start asking enough questions, you start to realize, all right, I can develop some kind of theory of the infinite, and I can use the concept of infinity in defining this thing we call calculus. But the answers I get are great, but they raise new questions, deeper questions about the infinite. And so the goal is not to, part of it's the thrill of the chase. People love interesting, beautiful theories, and this is a beautiful theory. It's just a captivating concept, these different levels of infinity. And if you want, I can tell you a few of the intriguing things about that. But actually, the desire is to ground mathematics, your mathematical theory, on a rock solid foundation.
Right.
Because you're translating data into math, you're doing math, and you're translating back into the real world. And if there's problems in the mathematical computation side, well, you can't trust your prediction.
Right. Exactly.
So let's make sure that everything we're doing mathematically is axiomatically rigorous,
as close as we can, given
and of course the desire is complete rigor.
Right.
Right. So let's push our axioms deeper. Let's examine it from every angle and make sure that everything we're using is completely well defined and specified and logically coherent. But again, the mathematical universe is a big one, because the real universe is a big one.
Yeah.
I was going to say, I talk about this in the class I've taught at NSA for sophomores, their mathematics colloquium. And so I said that there's more real numbers than rational numbers, not just like there's more, but it's a different level of infinity.
It's uncountable infinity.
It's uncountable.
Right.
What's interesting about that is that on the one hand, there's uncountably more, like vastly more. But if you look at every two real numbers, there's a rational number in between. And if you look at any two rationals, there's a real number in between. So in a sense, it's like interwoven like this.
Mm-hmm.
Okay, so that's there's like it's dense, right? So I'm not saying they alternate, but it kind of feels like that when you describe it, right? Between any two real numbers, there's actually a rational number.
Right.
So, and yet, although it has that structure, there are vastly more of these than those.
And it's
Right.
Yeah. What is the philosophical?
So many more that if you took every rational number and replaced it with you replaced each number with the whole set.
Each rational number.
If you took 1/2 and you replaced it with all fractions, and you took 1/3 and replaced it with all fractions, and then you counted those, it's still not enough to get to the real numbers. That's how much bigger it is.
Wild.
Right.
Yeah. What are the philosophical implications of an infinite?
God's big. Yeah.
Yeah.
One of my favorite verses.
Would you mind scooting it forward just a tad bit?
Yes.
I think that you're slightly out of focus. Yeah, that should be great.
All right. Yeah, no problem. I look better
In
that
focus.
way anyway.
Yeah.
Out of focus. Yeah. So a verse that I love when it comes to talking about infinity is Ecclesiastes 3:11, and it goes something like, "He has made everything beautiful in its time, and He has put eternity into man's heart, yet so that he cannot find out what God has done from its beginning to its end." And so I think as you explore these concepts of infinity, at a bare minimum, it tells you something about the universe God created and the bigness of it. We don't live in a small universe; we live in a big one.
Yeah.
Right, because we have a great God.
Yeah.
And it's incomprehensible, right? So if math is not everything, right? There's more to God than what math can say. And yet, if we just talk about math, we get to the limits of our our intuition, of our understanding so quickly. So how much more
Yeah.
God?
Do you buy the theory that the universe is infinite in kind of a
I don't know.
an uncountable way? Okay.
I don't know.
You don't know.
Um,
And perhaps it'll always stay that way.
sure. Yeah.
But we will never know.
I think it's quite possibly infinite. Yeah.
Yeah. How does mathematics kind of reconcile the dealing with infinite, unknowable numbers and equations, while at the same time trying to stick to rigor and the hard and fast rules that we've assigned or found?
Well, so what's interesting about math is that you can. Well, so there are math problems which you can study and try to find an answer to, and then you can use mathematical reasoning to show that there is no answer.
Right.
So you can. I don't know if this is related to what you're asking, but sometimes the answer in math is no solution. Right, and that's true when we're solving an equation. That can be true, but it's also true. A famous one the Greeks discovered is the irrationality of the square root of 2. So if you have a square with a unit on each side, like a 1 foot by 1 foot square, you try to measure the diagonal. That diagonal is the square root of 2, and so an early theorem is that's not a fractional number. That's not a rational number. Not just that we haven't figured out that it's actually 17 over 42 or whatever, but that it's can't be done. Right. So it's an impossibility theorem.
Yeah.
We've proved a negative. We've proved that that's not true. In more modern mathematics, one of the fun ones is the quadratic formula tells you how to find solutions of ax squared plus bx plus c equals 0.
Right.
Right. So you have this equation and you can find a solution. And high schooler students memorize that and forget it and then rememorize it in college maybe. It's not that hard actually to derive it and show why that's the right answer, geometrically even. And so you want formulas for solving equations, and you want to make it, okay, so we got the quadratic formula. What if we have a cubic equation? So we have x cubed plus ax squared plus bx plus c, or something like that. Turns out you can solve that with a bigger formula that you don't want to memorize. Okay, that's great. As I recall, doing that was important for navigation in the 16th century for doing calculations with degree measurements of a small angle. Anyway, so all practical stuff. But 4th degree polynomial, you can come up with an equation. 5th degree polynomial, so you say something x to the 5th plus something x to the 4th. An equation like that can't be solved in the same way. It doesn't have this algebraic representation of an answer.
Right.
Using the types of elementary functions like square roots and powers and logarithms and anything else that you want to come up with. So it's unsolvable in general.
Yeah. Are there any problems that arise out of that that need to be answered by a Christian worldview? That kind of God has created a world that we can't figure out.
Right. I mean, I think talking about the bigness of God is great. I think talking about the limitations, and so all right. So when we're talking about limitations of mathematics, or this is an unsolvable problem, or predicting the three-body problem, the motion of planets, that's interesting. I think it's good to get used to recognizing your limitations as a mathematician. And okay, so that's especially true in a world where we try to mathematize everything.
Right.
We try to compute everything. We use artificial intelligence. We use ChatGPT. Right. So we use Google. Whatever we're using, what we're trying to do, whether we think we're trying to do it or not, there's some kind of pressure on us to mathematize, to quantify, to predict and understand everything. And even looking at the basic foundations of mathematics, there's limitations. right? There's things that are seemingly paradoxical, and so there's a healthy dose of humility mathematically, or an appreciation for the greatness of God and the bigness of the universe He created. And let's translate that into the technological world, which is mathematical, and say, all right, if we struggle to understand mathematical concepts, or if we've shown there are limitations to what we can solve perfectly, well, let's carry that humility over when we're applying it to, creating artificial intelligence, or predicting this or that or the other, or giving health advice from a machine, something like that.
Yeah. What does that randomness, that kind of chaos, what problems arise from that, not only for, first for Christians, and second for non-Christians, as they're kind of trying to understand the world?
So randomness, yeah. So there's if you think about the word unpredictable as a proxy for randomness. So when we talk about randomness, I mean, we could say, is there some non-determinism in the universe? But we can also just say, is there something we don't know the answer to yet? So when if you flip a coin, you don't know if it's going to be heads or tails. Right. So this is like the simplest probability set, experiment. It's like flip a coin. Is it heads or tails? 50-50 chance. But when you think about that actual process, I suppose if you knew, the mass of the coin and its angular momentum, and the velocity at which you toss it up in the air, and then the density of the air and any kind of wind, you can imagine that it's actually it's not random, right? We could model it physically, and we could probably train a computer to pick a video of it and predict heads or tails, before it reaches the ground or something, right? So,
right.
But what we're talking about is a state of ignorance in ourselves.
Right.
And we have ways of quantifying that uncertainty. All right, so that's probability in one perspective. And so, yeah, how does that present problems for Christians versus non-Christians? I think in all cases we're trying to make predictions under uncertainty, but that's we're all in the same boat there. That's life. I guess again, humility might be the answer. We do very sophisticated things and make predictions with limited knowledge, but let's remember that it's just a prediction.
What would a predictable universe look like?
Well, I don't know. I've never been in one.
Yeah. Yeah, I'm just curious as far as because this also plays into the determinism thing. Mm-hmm. Understanding that we have the actions we take can have consequences, and the random we can do things that are not in the algorithm, for people who believe we are in the matrix. I
like Wendell Berry, and I forget which essay is it. Is it the Mad Farmer? I can't remember where he writes this, but at the end he says something like, every day do something that does not compute. And so I mean, I think one thing I like to think about is, we don't, or maybe my wife would say something I have to remind myself is, we aren't computable, right? Like we are unpredictable, right? There's a way of knowing another person. There's a way of relating to other people and to the world that certainly is not, not predictable algorithmic.
Yeah.
Right. And so to have a deeper form of knowledge that's, to know somebody is different to know about them. So to remember that, of course, in relationships, but even if we're doing science or technology or something like that, another favorite quote is from C.S. Lewis in his reflections on the Psalms. He talks about a poem and trying to describe, to put up show a poem to an audience of people who can't read. And he says, you can show them the poem, but if you don't know how to read, you can analyze the ink, you can analyze the paper, right? But until you know how to read, that that process of analysis doesn't tell you anything about the poem.
It's meaningless. Yeah.
But those of us who can read still contend that the poem exists.
Right.
Right. So there's a deeper meaning in the universe besides its mathematical description or scientific description. So yeah, I keep coming back to limitations and limitations of our knowledge and limitations of our technology. But I love that quote because it reminds us there's transcendent. I mean, there's many layers of meaning beyond a mechanistic or materialistic explanation of the universe.
Right. There's also an idea among more atheist scientists that if we can explain what is happening in the universe, then we kind of can explain why, in an odd sense, that this is happening. Is there truth in that? What would your response be to people who say that?
Well, I guess I would say, it's begging the question. Why can we explain what's happening in the universe is the real mystery, right? So, yes, we've tried to develop scientific theories and mathematical models, and we've gotten pretty good at it in one sense. And there's lots of surprisingly powerful things that we can do with just our minds, with our experiments, with our math. But instead of that being a reason to reject God or the transcendent, that's actually raises the question. How can products of random chance have such great answers?
Right.
Right. How can we develop theories that don't seem to make sense as the product of natural selection for one thing, right? Like the levels of infinity. How is that selected for survival? And if it is, why would we trust it?
Right.
So no, I don't think this materialist worldview can point to the effectiveness of mathematics and think that they've removed the need for the God hypothesis. I think it's the opposite. I think the fact that we have such power, even in the material world, raises the question of why, and that's the answer to a Christian. That's a question a Christian can answer.
But I'm sure they would say that the answer why is so that nature can survive and thrive and take over more. How does it point specifically to God?
Well, of course, we can blind ourselves and we can interpret the signs that God has put into the universe wrongly.
Right.
So it's not that a scientist can't look at that and draw any conclusion he wants to. But I believe that God has stamped his image on us, and therefore when we look at ourselves and then when we look at the creation secondarily, that we are seeing pictures of God, signs pointing to God, and in all the multifarious ways that happens. So there's some kind of God giving someone over to their ignorance, kind of Romans 1 style, or them choosing to not see what's there. And I don't know that scientific or mathematical argumentation is going to get to their heart in that way.
Right. And it's it's interesting because if you look at the universe in its chaos, kind of points away from evolution is what I would say, partly because everything's not efficient, and we don't seem to really be getting more efficient with time. And if the goal is what it seems to be, which is ultimate survival of the fittest, that comes along with efficiency, then surely we would be more efficient. And we don't seem to be getting more efficient, nor does it seem like getting more efficient actually brings about the right things. How does that randomness, how does all of the chaos point to a God who is very clearly ordered?
All right. Yeah. Well, so how does a chaotic world point to a God of order?
Right.
That's a good question. It's interesting that, there seems to be some back and forth about whether or not the universe is ultimately ordered as we look through history. Right. So, the Greeks looked up at the heavens and wanted to believe that there was perfection and that means perfect spherical orbits of planets that are moving at a fixed speed and all these things. And so there was this desire for order, but what they saw was disorderly, right? Retrograde motion, planets like moving and then coming back and moving and not seeming to go at the same speed, varying in brightness, brighter and less bright. And so you have this kind of tension and then Ptolemy comes along and synthesizes everything and says, no, look, it is orderly. And here's the order. Right. And then you fast forward 2,000 years and Tycho Brahe and others start doing really fine measurements with telescopes. And it looks like that order that we thought was there starts to break down. Right. And if you measure fine enough, the model thinks it should be here, but it's actually here. And you realize the universe is not, feels like it's not so orderly as we thought. And then you have a scientific revolution of some kind or conceptual revolution, and you see, actually, no. If we put the sun at the center and we have elliptical orbits, it's orderly again, and it's beautiful. And then you come along and you realize that it's almost elliptical, but it's not. Right. So there's a little bit of this back and forth, and to me that's the Ecclesiastes 3:11 thing, where God's orderly, and the order is there, and we see it in so many ways, and yet it's both. It's orderly because we have an orderly God, but it's abundant and full and infinite, and therefore it's not contained in some tight little system.
Right, an orderly God, when creating a universe, we see this even before Adam fell, that things weren't Adam had things were still chaotic before the fall.
Yeah.
How does I'm still not understanding how would an orderly God create a universe that is not like him?
Well, I think it is like him. I think God is also not deterministic and predictable. So, I think we have a better world than what we might naively call ordered, right? And it's like in a home.
Oh, absolutely.
Right,
Yeah,
right.
yeah.
Like you get married, you have children, and you thought you had all these routines that were great, right? And you thought you were going to go to bed at this time, and then all of a sudden you realize that that chaos is a real thing.
Yeah.
But it's so much better than the so-called order you have.
Absolutely.
Right. And so so is there order, and is a healthy home orderly? Well, yeah, it is in some sense, but a healthy order might be more complex than people walking around quietly doing their duties, right, with nary a smile to be seen.
Right.
And I think the same is true in the universe. Like we might say, if God is so orderly, why isn't the world more orderly? And it's because it's better than that simple order that we might expect naively. There is order, and that's why we have mathematical theories like chaos theory, right? That's why we have tools that actually can start to predict, we don't know this, right, because it's chaotic, right? And that's we've overloaded words like chaotic, but it's like it has this type of behavior that's hard for us to understand. It's maybe a better way to say it, right? But that doesn't mean it's disorderly. It just means it's hard. It's bigger than us.
It's more complex.
It's still ordered,
more
but it's
complex does not mean more chaotic. Yeah, because can you kind of unpack God is not predictable? Because and I'm playing a little bit of devil's advocate here, but surely a God who, we know that God is good, and therefore he always does good. Surely that would make him somewhat predictable, correct?
Oh, well, yes, of course. That's right. And God has revealed many things about himself to us, right? And but to say God is not predictable is not to say we can't predict or know anything about God. it's not. It's just that we haven't comprehended God, right? Like we haven't captured everything about him.
Oh yeah.
Right, and that's what I would say about the universe as well. To say that there's some chaotic so-called behavior in the universe doesn't mean that we don't know anything. It means we know so much, but we also have reached places where we can see more complexity than our minds can even grasp. And that's true with God. It's not that there's no order. It's not that there's no predictability. I mean, it's the same yesterday and today. But God's unchanging. All those things can be true without reducing God to
A mathematical equation.
a mathematical equation or an algorithm.
Right. Absolutely.
Right.
Yeah, because I talked a little bit earlier about the idea that if you had all the data points, you could predict the universe. Some people, atheists would say, and that is what God is he's just an infinitely large computer that can understand all the data points and therefore predict the future. How does the chaos that we see not point to an evolutionary world? Because surely that evolution is more chaotic.
Yeah.
Right, in the sense that it is less predictable. How would that not point to the world that we live in?
Yeah, and I'm not sure that that's exactly the way I would describe like evolution and chaos. I mean, evolution, the theory of evolution, one of the theories of evolution takes randomness as a significant factor, and tries to harness the power of randomness to create order.
Right.
Right.
Some order, but not ultimate order. Mm-hmm. Right, because in order to get to the highest, to win, more just to put it simply, you have to be a little bit unordered. I don't know that I'm phrasing this well, but like creativity requires a level of chaos. If everything was perfectly efficient and in its place, you wouldn't really be able to be creative because you would have to step outside of the bounds. Mm-hmm. For evolution to go from the single-celled organism to the highest form of life, whatever that is, requires some
mutation,
creativity, and randomness. Mm-hmm. And even at the top, you don't want full, complete order because you still need some creativity. Some randomness in order to potentially generate even higher forms of life. Well, correct?
I mean, so that's kind of a teleological view of evolution. Or I mean, what I mean is like you're saying, well, you need more space for creativity, and it's like if you're a materialist, if you're an atheist, the universe doesn't need anything. It just happens to be this way,
yes.
Right? And so maybe it's reached the end of its creativity,
right?
Right. There's no inherent need for there to be more. But I think where my mind goes with what you're saying is that an evolutionary theory actually claims that this randomness leads to greater order, right? Like we are increasing complexity via randomness,
and maybe not greater order, but greater forms of life.
Okay, sure. Yeah, is that more or less orderly? Okay, I don't know.
I'm not entirely sure either, but the point is to achieve a life form that will always win the strongest survives battle. And so
then again, you're using the words like should. There's no should.
This is kind of
what evolution could do is could observe that things that have traits that traits that lead to survival persist. Right? There's no should, but I know what you mean. Right? Yeah. We're kind of anthropomorphizing it or something. But again, what evolution describes is a process whereby increasing complexity arises through randomness.
Mm-hmm. Right.
And so, it's not that there's never a case where randomness results in order.
Yep.
But it's hard for me to believe that the fundamental principle of the universe is randomness, right? Which is kind of an evolutionary tendency.
Okay, yeah.
Right? And so that's not, I wouldn't say that. I wouldn't say that the fundamental principle is randomness. I would say the fundamental principle is order. But it's such a complex like infinitely complex order that we see all this amazing diversity of behaviors, mathematically speaking, and everywhere else. But at heart, I don't see randomness when I look at the universe.
Yeah, there's certainly an order to it, and I see where you're going with like, if everything was random, you don't even have the opportunity to, you don't like you have. There's a level of randomness at which creativity also goes out the window, just because you have to, like every random orientation, random mutation is just fighting to survive because it's so random. This is yeah. If the universe, and again, I'm arguing from what I believe is an evolutionist standpoint. I could be wrong, but if the universe is fully random, but is aiming at order on a large enough time scale, right? And currently we're at maybe it's 14 billion years according to them, whatever it is. We have gone from soup to here. I don't see how the current state of the universe can disprove that. Can disprove the nature of the universe.
So you're saying, all right. So I'm not exactly sure. You're saying, given that time span, 14 billion years,
right?
Given what we know about randomness, natural selection, you're saying maybe yes, maybe no. That's your answer, or that's the evolutionary answer? You're saying?
Yeah, I think that we are where we are right now does not tell us anything about the nature of the universe. We would have to observe things on a longer time scale, simply because that way we can see where we're going and by proxy where we are headed.
I see.
Right.
Well, right, and let's we haven't observed 14 billion years of
no, we haven't
the universe's history either. So we have a little bit smaller of a time snapshot than that we have to extrapolate out to all of the universe and history and the nature of things. So okay, yeah. So maybe an evolution would say, yeah, we don't know yet, and you can't disprove it. If that's where you're headed.
Yeah. In other words, how can we, currently, while looking at the current state of the universe that is observable to us, determine the overall principles on which it is guided?
Mm-hmm. So I'm not exactly sure if this is the direction you're headed, but I think there's an idea that some part of the universe is contained in a speck of sand, right? Like the laws of the universe that apply in a speck of sand apply to the distant stars,
right?
Right. So even if we aren't observing everything about the star, we can look here
and infer,
and we can infer, and we, even one of these assumptions that the physicists make, these symmetries that they posit are, the same rules that apply here apply there, right?
Right.
It's invariant to your location or whatever. I don't know how they say it exactly, but so if you want to hope to say anything about something that you haven't seen yet, something in the past, something far away, then you have to assume that it's something like what you can observe.
Right.
Right. So in that sense, I would say, okay, well, yeah, we haven't observed everything. But yeah, we have to believe that there's some consistency, and anything we see now applies.
Right. And I think they would say the exact same thing of like, but then they would draw the conclusion, okay, we can see the rules of the universe in a grain of sand.
Mm-hmm.
You can see the rules of the universe in a grain of sand.
Mm-hmm.
How is our rule different from your rule, and how are we both going to point to the grain of sand as evidence?
Mm-hmm. Okay. Well, I'm not a expert on proving or disproving evolution, but so a Christian mathematician approach to answering that question might say, what are the odds that we would get a universe like this if if we were dealing with randomness, right? So there's a big bang and things happen, and strong forces and weak forces.
Incredibly rare, yeah.
And then, okay, so let's do some simple probability. And there's this lecture that's out there by a guy named Steve Jeffrey.
But yeah.
Okay, yeah. He, I think he did a lecture locally here, a series of lectures I listened to one time, and I remember he went through some of those things. The probability that this force would be in the right range for life to form, and this balance of different elements, and basically his illustration was you end up like covering the earth with quarters. You want to pick out the right one, but that's not put an X on a quarter and then cover the earth with quarters up to yay high. And then if you want a universe like ours that can sustain life, the odds of that are like
super low.
Walk around the world, pick out a quarter, and you got it on your first try. And actually it's more like do that to the height of the moon and back a bunch of times.
Right.
So, okay, there's a randomness. Could it happen? Yes, but
statistically, but the lack of probability doesn't disprove it. Correct? Like, it is highly improbable that if, like, for Christians, that God would become a man. We would say that is highly improbable, and yet it happened.
I'd say that's impossible.
Right.
So
improbability,
but it happened.
Almost impossibility, doesn't disprove something. It just makes it. And if I know there are some evolutionists who believe that this is not the first go round of the universe.
Okay, sure.
Right. So how do we both look at the same set of pieces of data, that randomness, that chaos, and also the order, and we point to God, and they point to evolution?
Right. Well, I mean, I guess so. There's presuppositions that come into play, and if you have been enlightened, if you have the Holy Spirit, your eyes have been opened, God has called you to Himself, then I guess you see one thing, and if God has turned you over to darkness, then you see another thing. So
that's entirely fair. Yeah.
All right. So we could take a presuppositional perspective on that and say, well, we can make arguments all day long. Actually, I just finished teaching Euclid, which is all about axioms and the conclusions that follow from the first postulates. And if you have different axioms, then at some point there's going to be a different conclusion, right? Like you might have similar conclusions along the way, but at some point those are going to diverge. And if you find yourself disagreeing with somebody and you both are being consistent or logical and rational, then you have different starting points.
Right.
Absolutely. So at some point there's a hard issue of like, your heart's here, my heart's not, my heart's over here. Yeah. We're going to see things differently.
Right. Yeah. I'm sure we could keep going on this, but I'd love to go elsewhere. What are some of your favorite paradoxes? You mentioned the the ball bouncing is how I've heard it. That if it bounces half as high, eventually it'll never stop really bouncing. What are some of your other favorite paradoxes?
There's a lot of great paradoxes, mathematical and otherwise. I mean, there's the well. Let me tell you one that's a little different than like some of the standard, like the Barber paradox. All right, with Russell's paradox, let's there's one called the Ross-Littlewood paradox, and this has to do with ping pong balls. Sometimes I think it's even called the ping pong ball paradox, and you have a bag, an infinite bag, and you have an infinite number of ping pong balls, and you're going to do step by step. You're going to put in 10 ping pong balls to the bag, and then you're going to take one out. Okay. Do that forever. How many do you have? Right. Do that infinitely many times.
Technically, you have a finite amount. Unless
I'm saying do it infinitely many times.
Okay.
You have done that an infinite number of times. How many balls are there?
Well, there's an infinite number in there, and you've also taken out an infinite number.
Right, but I put 10 in every time, and I took out one.
Right.
So that's the paradox. I mean,
Yeah.
if you have an opinion on that, I would love to hear it.
Well, I just feel like a lot of these are just we're too small to figure it out.
Yeah.
Um,
Yeah, because so that the answer is what do you mean? Right. So you're right. You can analyze it in different ways and say, like, what do you mean by you've completed an infinite number of things? Does that even make sense? Because on the one hand, you've put in more than you've taken out, so there should be some there, probably an infinite number, right? You've basically added 9 ping pong balls an infinite number of times. That means there's infinitely many ping pong balls in the bag. But this is kind of one of those things that illustrates the quirkiness of infinity. So if you number the balls, and the first balls you put in are numbered 1 through 10, but then you take out ball number 1, and then you put in 11 through 20, and you take out ball number 2.
Okay, yeah.
And then you put in 21 through 30, and you take out ball number 3. Right? So again, in aggregate, you're adding 9 each time. But tell me a ball that's in the bag.
And if you do it infinitely,
ball 70 was removed on step 70.
Right.
Ball 70 million was removed on step 70 million. So there can't be a ball in there.
Right.
Right. So it's a paradox.
Yeah. So what do you do with paradoxes other than, is it just like this is kind of a cool thing we
Sometimes
have no idea?
I think it's just a cool thing.
Okay.
And
there's
or
nothing
at
wrong
least
with
it
that.
starts there. And then sometimes it actually matters how you think about infinity. Right. So it's the same answer as before. Like it's a search for rigor. It's a search for making sure this math that we do and found so much of life on. There's a lot of calculus. Calculus use infinity. Like we can't get away from it. We have to use the concept of infinity. So let's try to understand it if we're going to use it.
Yeah. Yeah, we've got to. I'm sure we could go for a lot longer, but I know you've got to go. As we kind of wrap up here, given all of what we've been talking about, what's your best piece of advice you would give to anyone watching?
Advice.
Yeah.
Learn more math. No, I love math, and I think math is bigger than often we give it credit for. That's true, and it's one of many tools to understand God, but it is a tool for understanding God. And so, don't just because you don't like the quadratic formula or you had trouble with 9th grade geometry or whatever it is, there's a lot there. And one of the big things that math through the ages has shown is just how big God and his universe is.
Yeah. And it's glorious. I was the Fibonacci sequence has always fascinated me. And the counting flower petals, the golden spiral,
sure,
and all those things. But it is, like, it's always chaotically random. This chaotic order. Yeah. Where can people find you online? If they want to learn more about these things, research on their own.
Right. Yeah, that's great. So if you look at New St. Andrews College's website, I'm on the faculty list there. I'm not teaching this semester, but I'm still up there, and I should probably update my bio. But there's an email address, brobinson@nsa.edu. I work as a data scientist and a researcher in computer vision and mapping algorithms. So you can probably find me on like LinkedIn or one of those sites. Either way.
There you go. I'll put links in the description.
Great.
Thank you so much for coming on the show.
Hey, thanks,
It's been
Jackson.
wonderful.
It's been fun.
See you guys.